Welcome everyone. My name is Mubashirullah. I thought I would present my project as a recording because 10 minutes are not enough, and then you can watch this extended version for your own leisure. So what is my topic? My topic is sentiment analysis of tweets related to vaccine. So what is the definition of sentiment analysis? It is the process of computationally identifying and categorizing options expressed in a piece of text, especially in order to determine whether the writer's attitude towards a particular topic, project is positive, negative, or neutral. So if you're working for a company, they might want to analyze the sentiments with regards to perhaps their new product. And this is where this project will come in hand. And you can go to my GitHub and pick it up and then modify the relevant bits and be up to speed with it. So I'm going to explain this in detail to you. And that is my aim. So if you ever had this task, you know exactly what to do. So firstly, I highly recommend that you read chapter 4 of our course book. It's very well written, it's very easy to understand, and it talks about some optimization techniques that you might find really useful. Right. So since I had to apply it on tweets, I had to collect them. And in order to do that, you need to be familiar with the developer API from Twitter. You need to be familiar with Tweepy. And the Tweepy library is the documentation is very easy to go through, and I highly recommend you go through it. So you come here and you make an app, and that needs to get verified. So if you're working a day before the project, then things are bad for you. So what you really need are these keys and tokens, and don't expect a friend to give them to you. Get your own. You can regenerate them. So once you get these API keys, just save them in a file, and you are ready to collect tweets. So I won't get into the detail of how all of this works. It's pretty easy, and what you can do is take this file from my repository and just change the following lines, vaccine or vaccination, and enter the query that you want. Perhaps you wanted a particular topic, and this is where you would need to go through the developer documentation and figure out how you can write a query. It can be quite more advanced than this. So I didn't need retweets, and I wanted it in English, and I wanted the extended version. That is, I wanted 280 characters. So I wanted the whole tweet. And this gives me the tweets. So it seems quite simple, but it takes a day or two to go through those documentations. And the next task was simply to save them in an Excel file. It looks kind of complicated, but what I've done is that I decided that maybe I want to collect more tweets in the future. So I wrote the code to, be able to append to the Excel file. And I've given a few links over here that I think you will find useful. So with that done, you've now collected your tweets, and we're done with part 1. Now let's move to labeling tweets. So it's very important for you to define a criteria on what qualifies as positive and negative and neutral, especially if you're working with a team and you've divided this task, if you're labeling as a group, because you want all of you to be on the same page. And even as a single labeler, I found this task quite difficult because some tweets were really ambiguous. So that's where the idea of a third class comes. It can really help, So positive were pro-vaccine sentiments. An example is, I literally cannot wait to stand in line for my COVID vaccine. A negative I termed as all anti-vaccine sentiments, conspiracy theories, they would all come into this class. So the example of that is Joe Biden, tell that to Bill Gates and his depopulation scheme and his vaccine. So there's a lot of criticism. There's a lot of conspiracies against Bill Gates. And it's fun to hear, but they're kind of dangerous as well. So where this project becomes useful is that it would give an idea to the ministry on the extent to how much misinformation is out there. And the dual purpose of this is also that since it can classify negative tweets, it could help moderators better moderate social media. And you may have heard that Twitter and Facebook, they are deleting nonsensical posts. So with that done, I simply, you can label your tweets on Excel. You don't have to write a program like I did. I just found this a lot easier to do. And let's just label a tweet right here, right now. Wait, I have to run the whole file. We'll just label one to give you an idea. NumPy is taking time. Right. A coronavirus vaccine could be the first that outwits nature. Now, this doesn't make much sense to me. Is this pro-vaccine sentiment? Is this negative? Fun fact, I've actually read this article, and this is actually the headline. A coronavirus vaccine could be the first that outwits nature. This doesn't tell much as to whether it's positive or negative. So should we make it neutral or positive? See, it takes so much time to label tweets. I've spent 8.3 timers, and I'm still not all the way through to 500 tweets. It could be the first that outwits nature. Yeah, let's go with positive. And that example is enough. Right. So each time it saves to the original file, and here's an idea. Right. With that done, we're done labeling tweets. We can now move towards the model program, and let's just rerun the whole thing. Because I've labeled one more tweet, I want that to be added to the result. Right, so what do we have here? There are a number of machine learning classifiers that can help you. In chapter 4 of the book, they focus primarily on naive Bayes, and that's a wonderful classifier. It can, to a great, it's really intuitive. It's not that difficult to understand, and doing multi-class with it is also very easy. What this book also tells you about is an optimization technique, and that's called binary naive Bayes, also called multinomial naive Bayes. And the idea is to reduce, take only the unique occurrences of words per document. So this reduces the frequency. The idea is that the occurrence of a word is far more important than the frequency. Two other ideas also mentioned in this optimization part is to do negation. This is the idea that, process your text such that if you didn't, just append not to all words that come after it until you come through a punctuation. So I didn't explore this idea. And a third idea was to use something called sentiment lexicons. So really a lot of, reading really helps you get an idea, so you don't have to go through a lot of other research papers. It can go in many directions. I hope they ran this. Right. So let's start here. Right. So first, I I run the program, and I collect the tweets. And here is, it's very easy to read tweets, read an Excel file in pandas. And let this run a bit, and I'll show you the output. And until it does run, let's talk about pre-processing. So it's very important to change your tweets into a normalized form. So what are the processing techniques I applied? I lowercased all the letters, that's easy to understand. I normalized the URLs. So each tweet had a different URL. It doesn't make sense to keep count of them. So what you do is you change all URLs with a single keyword, say HTTP URL. The same technique you apply to tags and email addresses, because they two are unique, so it doesn't, there's no benefit into having them. Then there is normalizing numbers. Numbers could mean anything, so you convert it into a feature called num. You do the same with the $sign. Then we do word stemming. We normalize punctuation. What do I mean by that? So there's something called TypeScript punctuation. And you want your program to be in the normal punctuation. You want to expand contractions. So contractions are things like aren't. This will change into are not. And so this part you hard code, and I took this from GitHub, from Stack Overflow. I didn't write that. You de-emojize. This was something optional I did, because I thought emojis had information in them and they should be included in my tweets. At last, I removed punctuation. There were other ideas, like the negation idea we just went through over in the optimization concept. And there's also an idea of removing stop words. There's somewhat of criticism against removing stop words because they might remove information as well. So this is the code for it. It's pretty simple. You lowercased it. You replaced the HTML tags. We didn't have HTML tags, but I coded this anyway. I've removed tags. So the fake Donald Trump would become ID ADDR. Email address would become standardized email ADDR. Links would become HTTP ADDR. Numbers would become number. Dollars would become dollar. This is the code for normalizing punctuation. And this is for contractions. This is for de-emojizing it. This is where I remove punctuation, and at last I stemmed the program. I used Porter Stemmer. You could have used something more severe or stricter like Lancaster Stemmer, or you could have also used lemmatization. Porter Stemmer gives us good results, so it's good enough. Right, the file has run, so this is what a data frame object looks like. We have tweets, we have positive, negative, and neutral as numbers. So notice I labeled them as one hot encoding. I didn't have to do that. I didn't know why I did it. I thought because that's the output we usually convert it into when we feed it into a neural network. It turns out that scikit-learn programs actually want them in the categorical form. Right. So you notice that we have far less negative tweets. We have a lot more positive sentiment and a lot more of neutral sentiments as well. And that makes sense because people really want a vaccine. But notice, even despite this horrible pandemic, there's people still out there who think vaccines are just a big conspiracy, a get-rich scheme, and all that sort of nonsense. Right. So here we processed. So here we got the tweets, and here we got the target. Target is the labeled. This is also called golden labels. And having gotten those, you make a train and test split. This is a function in scikit-learn that does it for you. And I stratify the target. This is an idea that if your classes are not even, you try to make a distribution such that they represent the distribution that's actually there. So if I have less negative tweets, the test set would also have less negative tweets. So let's move to part 3 as making a feature vector. Right. So in case of a naive Bayes, which is right here in the end, you can just enter in the tweet words, and you can make a count vectorizer that will train on your text. Then you transform your tweets, and then you just feed it into the program, and it will train and run for you. And it's pretty straightforward. We're getting a test result of 0.6 or 60 accurate on the test set. And accuracy isn't just a good, it's just one number. To give you more detail, you would rather want to print a report. It gives you an idea of how the classes are faring. In case of these other machine learning algorithms, I needed to make a feature vector because I could not just input the words right in. So how does this work? Well, take all the tweets you have, all the tweets in your training set, and make a dictionary where the words are the keys and their frequency are the values. And then take the most common of these, the most common words in your set, and then that becomes your feature vector. So what you do next is you take a particular tweet and you ask yourself, are words in this tweet part of the feature vector or not? If they are part of it, you assign a 1 to it. In Python, 1 and true are the same thing. If it's not part of it, you assign false into it. So you make a 200-word feature vector, and each tweet transforms into that feature vector. So I hope you understand what this means. It's easy for me to understand. So you end up with a feature vector, and here's an example of it. A 4 by 200. So each tweet is now a 1 by 200 feature vector. What I do next is I save this as a CSV file, so I don't have to process this again next time. And so I can use this later on. And when we move on to neural networks, I just import and I just read it from that CSV file. So we come to support vector machines. Support vector machines is about maximizing the margin. It maximizes the minimum distance between the hyperplane and the data point. If that doesn't make any sense, go read about it. What I really like about support vector machine is that it's a linear classifier, but you might have a data that requires a non-linear classifier. This interesting idea with support vector machine is that you can take a kernel and you transform that data into a hyperplane. You transform it into such a format that a linear classifier can then be applied to it. So this gives inspiration that maybe we can convert one problem to another form whose solution you already know of. So I found that quite inspiring. So here we initialize a linear support vector machine. We fit it with the training set, and it scores a 98% accuracy on the training set and a 48% accuracy on the test set, which is pretty low, pretty low. And here we can see that it's doing very bad on the negative. It's not performing well at all. Here are other examples of support vector machines with different kernels. So the above one was also linear. There's actually a mathematical formula difference in linear SVM and SVC with linear kernel. It's performing much better on the training set as opposed to linear SVM. And a kernel with poly is performing even better with 57% accuracy. So let's now move to graphical hyperparameter optimization. So notice here that C equals 1 is a hyperparameter, but the default is 1. Changing these hyperparameters would change your results. And one way of knowing what hyperparameters to use is just trying a list of them and plotting the results. And that's exactly what we've done here. You can see train and test set are pretty much together, so long as their points were 0.001. But after that, you start overfitting. You do excellent on the training set, you do very poorly on the test set. Another idea of finding the hyperparameter is using grid search. Using grid search with cross-validation. Cross-validation is this concept that you go through your data set and you split a part for training and you split another part for test. And then you do this again a certain number of times, where you take another part as a training set and there's another part as a test set. And by the end of it, you've pretty much gone through your entire data. And this gives you a much better idea of what hyperparameter is more accurately going to give you a good result. So from the graph, 0.01 would be, the graphical representation might sometimes mislead you, whereas grid search with cross-validation will give you a more accurate result. Now let's move to part 5, K nearest neighbors. I've used a number of classifying models. K nearest neighbor is non-parametric. So the new example is compared to the entire data set, and the shortest distance of the K classes is considered, K being the nearest neighbor. So when you say one nearest neighbor, you tell them, okay, what was from among the shortest distances, the shortest one class that this data is closest to, you should assign class to that. It's pretty intuitive, and it makes sense of how you can expand this to a multi-class. So again, I'll repeat it. One example is compared to all the examples in the data set, and the ones that are closest in distance becomes your class. So if you have 3 classes, you take into account three distances it is closest to, and the most common occurring class, say 2 were positive and 1 was neutral, you pick up the most common one and you say, okay, this new example is positive. So K nearest neighbor also seems to do poorly on this one. Given I've labeled a different number of tweets, K nearest neighbor has done 62% accurate results. By giving it more results, it seems to have done poorly. So it's not conclusive. Then the other part was naive Bayes. So I tried naive Bayes with my own feature vector, the one I made above, and entered into all of these other programs. And then I tried the multinomial naive Bayes, where I gave it the data directly and let it do count vectorizing. So the naive Bayes model with a Gaussian kernel gives me an accuracy of 45%. It does a great job on positive tweets, somewhat of a poor job on the negative tweets. So it seems that what we care about, we're not doing well on what we care about. And that's the end of the machine learning algorithms. Then next, we'll move on to a neural network. Before we do that, here are a few other ideas that I could have done. And one was sentiment lexicons. I've referenced a paper to it. Right. So you can run this Jupyter notebook by clicking on it. Even if you don't have an account, it will, I'm pretty sure it will run for you as well. And you can play around with it. And you can tune the hyperparameters and see if you can improve the test score and the training score. So I've made a very simple neural network architecture where I have 3 classes, and they are fed into a sigmoid activation. And what sigmoid does is it calculates the likelihood of each of those classes and then gives me the one that is most probable. So I mentioned saving my process data as a CSV file. So here you can see I've uploaded it on GitHub, and here I directly read it. So this is the main part. I've used the Keras framework. It's a high-level framework for creating neural networks. You will find its use in residual networks, where the networks are really deep. And if you had used something like TensorFlow, then you'd realize TensorFlow is a low-level framework compared to Keras. So I just had to specify I want 15 layers, 15 hidden units in the first layer, and I want a ReLU activation. I want you to regularize it, L2 regularization, and I want you to initialize with Xavier initialization. If you initialize your neural network with 0, you will end up with a problem of not breaking symmetry, and your neural network then doesn't learn anything because all values turn into 0. In this second layer, I have like 3 units, and this activation is softmax. Again, the kernel regularization is 0.01. I'm regularizing the results so I don't overfit. So ADAM is an optimization technique. Momentum is another one. RMS prop is another one. You enter the loss function and you just run it. So a few other hyperparameters are batch size and epochs. So you have stochastic gradient descent, where you look at one example and then you calculate the loss and then you backpropagate through your neural network. On the opposite side, you have batch gradient descent, where you look at the entire data set and then you make one move, which is more accurate. And the middle ground is mini batch gradient descent, where you look at a certain subset of the data, say 64 or 32. And what this does is it employs the benefit of parallelism, but it also gives you more steps. So you take a lot more steps in one epoch. An epoch is going through your entire data set. So let's run this and see how our algorithm fares. You can see the accuracy starts at 57%, and this is on the training set. And you can see it gradually gets better and better. I encourage you to practice setting the hyperparameters. I encourage you to try a smaller batch size and then also reduce the epoch size as well. So it doesn't take long to train, and I get an accuracy of 56% on the test result, which is again pretty low. So if you have a low accuracy on your test set, usually that means you need to make a bigger neural network, try more hidden units, and try better optimization technique. In case of doing poorly on the test set, you have then a variance problem. Doing poorly on the training set is a bias problem. Doing poorly on the test set is a variance problem. So if we get a 97% accuracy on the training set, this means we don't have a bias problem. We have a variance problem. And variance can be solved by doing regularization. And we've done that, and I've tuned with it. It didn't really help. Another solution for dealing with variance is getting more data. And you can see I'm pretty much down to 60% accuracy. Multinomial naive Bayes gave me that accuracy. And these other algorithms are pretty much close to it, around 50%, 52, 60% is where the range has been. So I think if I collected more data, I might get even better test results. Yeah. Thank you.